Hello, everyone. Thank you very much for having me here. Uh, I'm very happy to present my recent research work and also see some friends here. Actually, I have some high school college, classmates working in Texas A&M. Uh, I will share you with my recent research on design-based causal inference in bipartite experiments. This is a joint work with several students in Berkeley and some a collaborator from Chinese University of Hong Kong. We posted the paper on our archive in January, but we haven't submitted the paper yet. So if you have some comments, please let us know, and we will try to incorporate the comments and polish the paper. Let me introduce the background. What's bipartite experiment? I don't think it's very standard in statistics literature. Give you some motivations why we care about it. And first give you the graph, the bipartite graph, and to show you the mathematical structure, then give you more concrete motivation. Basically, we are interested in this setting. We have two types of units. We call them intervention units and outcome units. I will tell you why later. The units, the two sets, the units are connected via this bipartite graph. And we will do experiment. We will assign treatments to one set of the units, treatment control, and we will observe the outcomes for another set of units. We call them outcome units. So there's a funny graph here. I will use this terminology later. It's called bipartite experiment because of this bipartite graph. We randomly assign treatment on the left-hand side, intervention units, and measure the outcomes on the right-hand side, called outcome units. Like, why do we care about this setting? Let's go back to classic setting. Classic setting is kind of, the first one is trivial setting. When we run traditional experiment, we randomly assign treatment control, taking the drug or not, to the patients, and we measure their outcome. So the intervention units and outcome units are the same. There's no difference, okay? The second example is also classic, not so trivial, which can be viewed as a bipartite experiment. It's called cluster randomized experiment. So the intervention units are clusters. For example, classrooms. We have a new device for teaching on the classroom level. And we measure outcomes for the students. Okay, the students are the outcome units. In public health, the intervention units are villages, and the outcome units are households. Okay, I think there's no one-to-one mapping, sorry. Should be classroom, students, and village and household. Okay, so that's a traditional cluster randomized experiment. Each cluster can be connected to multiple outcomes, whereas each individual can be connected to only one cluster. Okay, this is simple. And we want to extend the cluster experiment to bipartite experiment. In this graph, if you still remember, each intervention unit can be connected to multiple outcome units, and each outcome unit can be connected to multiple intervention units. That's the interesting feature, more complicated than the cluster experiment. Okay, still, why do we care? What are the more concrete examples we care about? The first one is from biostatistics or environmental study. Ziegler and co-author were interested in the effect of installing some air pollution reduction system on power plants, on the downstream effect on hospitalization rate, measured by maybe county level data, is the nearby areas. So the intervention units were power plants. Okay, the outcome units were the neighborhood, county level hospitalization rate. So you can imagine here, it's different from the traditional randomized experiment. We don't measure the outcome of the power plants directly. We measure the outcome of nearby neighborhood. Okay, that's one of the first example we care about. Second example, third example from the modern online digital experiment. For example, Facebook were interested in launching a new feature on the Facebook groups. They are interested in the downstream effect on user engagement. In this example, the intervention units are Facebook groups. The outcome units are users. Okay, so you can imagine one Facebook Facebook group has multiple users, and the one user may be in multiple Facebook groups. This is the bipartite graph structure. Okay, the treatment is the new feature or not. The outcome is measured as user engagement. This is the Facebook experiment setting. The last one is also from online digital experiment, motivated from Amazon experiment. Okay, the treatment is the new pricing strategy or not. This is the treatment assigned on Amazon items. And the outcome units are the customers. And the outcomes are measured by satisfaction level. Okay, so you can imagine, we can draw a bipartite graph between Amazon items and the customers. Okay. Is this part clear? Like, why do we care about the bipartite experiment? Yeah. Okay, your question is this new or not? Actually, it's not new because these papers already introduced this bipartite structure already. Okay, but this is not that standard in classic experimental design literature. Okay, because in traditional agricultural, industrial, or medical trials, it's hard to imagine why we have this structure. Yeah, but the recent online setting is quite common because it's two-sided market. We have the platform of the users. Yeah, you can imagine that another motivation is YouTube. We have producers and viewers. Each producer may have multiple viewers, and as viewers, we view multiple producers' videos. So there are a lot of examples like that, especially in online digital experiment. But we do find motivation from more traditional biostatistics.
Very naive question, but in all these examples, it's like from the practical perspective, it's sort of begging to include, not to have it actually bipartite, so to have interaction between users, let's say, right? So how essential is?
Yeah, that's a question of interest. Because of this bipartite structure, we worry about spillover effect interference. That's usually ignored in like the traditional trials. I mean, we worry about it, but usually we don't deal with it. Like in medical study, our outcome depends on our own treatment. Now our outcome depends on all the intervention units we connect to via this bipartite graph. Yeah. So thank you for the question. Okay, we want to do more formal causal inference with bipartite experiment. We introduce some notation. We use potential outcomes to define treatment effect. Here we have m intervention units receiving treatment. In the simple case, binary treatment control, zk, k from 1 to m. We have n outcome units. We measure outcome yi, I from 1 to n. Okay, and we have potential outcome. What's potential outcome? Hypothetically, if the intervention units have treatment z1 to zm, this vector z, unit i's outcome would be yi, z. Okay, so there are a lot of potential outcomes for each unit because in the most general formulation, my outcome may depend on all the treatment status of the intervention units. So I have 2 to the power of m potential outcome. There are a lot of potential outcomes in the original formulation because at this point, we don't know how to simplify it. Okay, just a large number of potential outcomes. But we ask a simple question. We ask a question on total treatment effect, and we think it's a policy relevant parameter. We ask, what if all the intervention units receive treatment versus what if all the intervention units receive control? Okay, how would my outcome change and average over all units? This is the tau, the total treatment effect. Okay, hope you are okay with the notation. Average over all units, the potential outcome indexed by vector 1 and vector m. Vector 1 and 0 with dimension m. Okay. This seems a lot, but if you assume this, we go back to the traditional setting. The traditional setting, m equals n. The intervention units are identical to the outcome units. And the traditional literature assume my outcome only depends on my treatment. That's yi1 and yi0. Very simple, two potential outcome. And we compare yi1, yi0 average over units. That's the traditional average treatment effect. Okay. So just want to convince you there's no surprise if you go back to traditional literature. Okay. In the traditional literature, this is the assumption called sattva, called stable unit treatment value assumption. Basically says there's no interference. My outcome only depends on my treatment. Okay. But here in this formulation, my outcome depends on everybody's treatment. Okay. So let's move on to make some progress. At this point, it's only definitional, no progress at all. Okay, we make some progress because we have a bipartite graph. We want to simplify the potential outcome structure. Otherwise, each unit has 2 to the power of m potential outcome. That's too many. To make progress, we want to simplify the potential outcome based on the graph structure. Some features on the bipartite graph, we use G to represent the graph. G is binary, 0, 1. If GKI equals 1, if outcome unit I is connected to the intervention unit K, otherwise 0. Okay, the graph adjacency matrix. Some other notation, we have outcome units. Okay, fixed intervention units. Unit K, we have this fancy GK plus. This is the set of outcome units connected to the intervention units. And this cardinality equals GK plus. Hope this is a traditional matrix notation, fixed summation. Okay. For the outcome unit, we ask what are the intervention units connected to unit I. This is also the curly G plus I is the set of intervention units. This is the cardinality G plus I. Okay, so the graph notation. Then with this notation, we simplify the bipartite, we simplify the potential outcome notation. We assume yiz equals yi, the subvector, z indexed by the intervention units corresponding to unit I. Okay, so on the graph, you have unit I, you just look for those intervention units. Okay, we assume my outcome only depends on the intervention unit's treatment status. So it's a subset of Z. This is the subvector notation. Now, the total treatment effect, tau reduces to slightly simpler notation because this is yi depends on all ones corresponding to the intervention units I correspond to. Okay. This notation is a little vague because this only says the dimension of my potential outcome, but actually more than that. It's dimension also those intervention units. The notation can be vague here, but you can see the complexity still. It's a vector. Also, the dimension varies across units. Okay, but it still have this interpretation. What if all the intervention units matter for me, get treatment versus get control? Okay. So please ask me questions because the initial section is notationally heavy. That's right. That's the whole game here. Traditionally, my outcome only depends on my treatment. Now my outcome depends on multiple intervention treatment. You can imagine, like for a county, it may be affected by multiple power plants nearby. That's the motivation from the biostatistics example, because maybe the direction of the wind will be random depending on the time. So, and one power plant will affect multiple counties. Here, kind of implicitly, we don't really assume it, but implicitly is all the ones and all the zeros. Yeah. So I think here is more implicit. Does not matter that much. For example, if we assume, some people may assume may assume y depends on the proportion of treated units. In that case, it's more explicit, saying we don't care about the intervention units. Because of this all ones and all zeros formulation matters less. I will give you example, maybe M you can imagine like maybe 200 and maybe 700. That's the magnitude. But it depends, like in Facebook example, Amazon example, M and then can be super large. Yeah.
You can also think about it as a random environment connected to a lot of mathematical models. So you treat the environment and the environment propagates.
Yeah, yeah. If I understand your question, you are saying you want to model G or like what's random?
Not random, I mean, so the interference factors, it's just environment developed around the outcome factor.
That's right. That's right. That's right. This is bipartite. Sometimes you can represent some spatial data in terms of bipartite graph. There are some examples having spatial. Actually, our example has spatial structure, but we reduced it to the bipartite representation. Okay. Okay. Let's continue with the discussion. Okay. Now, at this point, nothing is random yet. We just introduce a bunch of notation. We have fixed intervention units, outcome units, fixed bipartite graph, and imagine all the potential outcomes. So far, everything is fixed, no statistics at all. Want to do statistics, what's random here? There's only one random part in our formulation, that's the random assignment. That's why we call it design-based inference, because the inference is driven by the design. Okay, the design is we randomly assign treatment control, new feature or not, or the pollution reducing system or not, to the intervention units. We assume Z1 to Zm are RID, are Bernoulli random variable. It's the simplest possible experiment you can imagine, just coin tossing. Slightly different from, if you are familiar with the literature, some people call complete randomization. They mean they have permutation of ones and zeros, the fixed number of treated and control units and permutation assignment, but we assume RID Bernoulli. But it does not matter because the RID thing and the permutation are very similar by a coupling argument. We can extend the discussion to heterogeneous treatment probabilities. For example, ZK have a different probability PK. One leading example is stratified experiment. You stratify your assignment based on the features of the intervention units, depending on their covariates. Then PK can vary across the units, the intervention units. But I think the extension can be simple in this case, conceptually simple, but you need to do more because later we will simply run inverse probability weighting. So you can easily extend the weighting estimator to heterogeneous probabilities. Okay, let's focus on the simplest possible setting. Because this setting is already interesting enough as a first project. Okay, let's continue. How do we do statistics here? How do we estimate the parameter of interest, tau, the total effect under this randomized experiment? This is our point estimator. There's no surprise if you are interested in parameter like this in a randomized experiment. You do inverse probability weighting. You just use, if you look at this Y1, how do you get information about this Y1? You can only get information from those outcome units connecting to all treated intervention units. How do you get information about this Y0? You can only get information from those units with intervention units receiving control. Okay, there's no surprise because in some sense we are doing non-parametrics here. There's no additional information you can use. Okay, you only use units I with Ti equals 1 and Ci equals 1. Ti equals 1 means all the intervention units connecting to I receive treatment. All the intervention units connecting to I receive control. No surprise at all. And this is just inverse probability, the probability this event happens. You mean like what if there's no units receiving all ones and all zeros? Yeah, exactly. So you can imagine here, you must have enough units with ti equals 1, enough units with ci equals 1. In some regime of the graph, this event might have probability 0 or close to 0. You will see the mathematics will reflect this intuition later. Okay. Yeah. If you look at this formula, you already see it's possible this estimate is easily defined. Yeah. Here, we work on the setting. This is well defined, and I will tell you, it's well defined, and we want to analyze it. Its property depends on the graph structure. If you imagine if everybody is connected to everybody, if I'm connected to all the intervention units, this event has a probability almost 0, because it decreases to 0 exponentially fast, depending on how many intervention units I'm connecting to. Okay, you will see the mathematics more precisely. Okay, we focus on Hayek, which is a little ugly here. Some terms here to normalize the probability, but you can ignore it. You can go back to the Horvitz-Thompson estimator, but usually it's worse than Hayek. And but the theory for Horvitz-Thompson is actually simpler. Okay, is this part clear? Very simple estimator. You are interested in comparing all ones versus all zeros. Just give me all the units with all ones and all zeros. That's it. And because those units are not the simple random draw of the whole population, you need to do inverse probability weighting, because different units have different probability of receiving all ones and all zeros. Okay. So we want to analyze this Hayek estimator, asymptotic analysis. What do we mean by asymptotics here? As I was saying, we have fixed graph, we have fixed intervention units, fixed outcome units, fixed potential outcomes. Only IID draw of the treatment indicator are random. And now I'm talking about asymptotics. What do we mean? What do you think about what will diverge, what will increase? Okay, here we focus on the regime. The choice of the regime is not unique. Here we focus on one regime, M diverge. What's M? M is the number of treated units. Okay, because that's the only source of randomness. If you want to do asymptotics, CLT or those limiting theorems, you need to have enough random variables. ZKs, the number of ZKs will diverge, obviously. Okay, the randomness is driven by ZKs. And we allow N also diverge with M, but it's not arbitrary. There are some restrictions. And the bipartite will grow. Okay, the dimension of the bipartite will grow. Then what do we mean? Like there is a sequence of bipartite graph, and we don't specify a model for the bipartite graph, but we will specify some condition on it. Like this, you will see later, some sparsity condition on the bipartite graph. The graph grows, but not arbitrarily grows. Intuitively, we must have enough units with Ti equals 1 and Ci equals 1. That's the question asked just now. Otherwise, there's no hope. We will have law of large numbers and central limit theorem. Okay. Then this must depend on the sparsity of the bipartite graph. You will see conditions later. Okay. But there is another condition which is not that interesting in our setting, is the moment condition on covariance and potential outcome. And for simplicity, just assume you have bounded variables. You don't worry about outliers for CLT, because we think the sparsity condition is more interesting in our setting. Okay, first, the consistency of the Hayek estimator. Tau hat converges to the total treatment effect tau if we have two conditions. You won't be surprised by the conditions if you read them. Okay, the first condition says for outcome unit I, the G plus I is the number of intervention units connecting to outcome unit I. You look at the maximum intervention units for all the outcome units. This cannot grow too fast. Otherwise, I'm affected by too many intervention units, then there's no CLT at all. Okay, this is constant order. And maybe someone suggested the name of no super receiver. Okay, if I'm a super receiver, I'm affected by everybody. Okay, can I have CLT anymore? The other one is the other direction. For every intervention unit K, you count how many outcome units connect to it. The maximum number of outcome units can grow, actually. We only assume it's slower than n. It's good enough. Okay. Why do we have asymmetry? Because the formulation of our model only have randomness on the z part. Only the intervention randomization part is random. We're conditioning on the potential outcome. So there's an asymmetry. The sparsity on the maximum number of intervention units is more important because the randomness of z drives the limiting theorem. Okay, this condition we call it a no super influencer. Okay, but it's weaker than the first condition. There's no treatment unit affecting too many outcome units. Okay, C is also restricted. How do we get this condition? It's not that hard. If you prove limiting theorem, you just want to ensure the variance is going to 0. Okay, by Markov inequality, you have to ensure the variance is small, and the variance goes to 0. You will see these conditions will appear naturally. It's reasonable for the power plant example because you can imagine due to the spatial restriction, one power plant will just affect a few counties nearby, and given a county, it will be affected by the nearby power plants. It won't be affected by all the power plants. Okay, but it can be subtle for other settings. For example, the Amazon, the online setting, maybe in their setting, like one product will be connected to many users. Like for every user, we will buy a lot of products. Can be subtle in their examples. That's why in this paper, they talk about bipartite experiment. They impose a model assumption because otherwise you cannot make progress. They basically assume a linear function. My outcome depends on the proportion of treated intervention units as a linear function. That's what they did. Okay. Here we want to do more non-parametric analysis, but the restrictions we only talk about all ones versus all zeros. So there they can talk about those response curves. Okay.
I believe that the outcome wise, we are not making any state parameter assumption or anything like that right now.
No. Actually, they're not random in our formulation. We condition on them. Even if the potential outcomes are random, we condition on potential outcomes. So we don't want to deal with them, basically. We only derive limiting theorems condition on everything except the i's, the case. Yeah. Yeah. Condition on the potential outcomes. Yeah. That's why it's called design-based inference. Some people like it because they feel they only need to think about the randomness from the design. They don't worry about the outcome. Some people don't like it because they feel like all the statistics models are modeling the outcome. So like suddenly you are saying don't model it, just condition on it. But depending on your feeling. Yeah. Yes, the G is fixed in our formulation. It's fixed. We know it. We observe it. Yeah. Because otherwise we cannot compute the estimator. You can see the estimator depends, of course, on the G. It's fixed. Okay. Second, asymptotic normality. Unsurprisingly, you can prove asymptotic normality if you standardize your estimator under another two conditions. With the first two conditions for consistency, of course, more restriction on sparsity. If you want to get asymptotic normality, the first condition, how do you read it? If you fix intervention units K, you count how many intervention units are related to me, How do you define it? If we are two intervention units, we are connected if we have a common outcome unit. Okay. We count the maximum, we count the number of connected intervention units for each intervention unit, and we assume this number is bounded. Okay. It's stronger than the sparsity we imposed before, but you can allow B to diverge actually, but slowly. We don't worry too much, just assume it's bounded, absolute, constant, can diverge, but just technical. Another sparsity condition on the bipartite graph. Because otherwise, the spillover is too strong. You can imagine there are some graph, all the intervention units are connected indirectly via another outcome unit. This assumption breaks down. Okay. Again, it's reasonable for the power plant example due to the spatial pattern. There's no the violation of this assumption. But if you worry about these sparsity assumptions on the graph, then it's very possible you cannot do anything with this parameter. Okay, this parameter is very non-parametric. You cannot do much without this sparsity assumption. You should modify your parameter of interest. I will talk about it later. Okay. Second condition is more involved. It depends on the sparsity condition and also the variance condition. It's quite a convoluted statement of the assumption. It requires the degree of the graph does not diverge to infinity too fast. Also restrict the variance does not converge to 0 too fast. Okay, I will give you examples to make it more transparent. This one is a little dense now. But to explain this condition, I need to give you the formula of Vn. Okay, Vn is the symptotic variance. First give you the variance formula, then discuss this condition. Okay, we define centered potential outcome. We center each individual potential outcome by the average, and we vectorize the potential outcomes as the vector of all units potential outcomes. We also define n by n matrices depending on the bipartite graph. It's n by n because it's depending on the units. Okay, this is the notation. Fancy G plus Ij is the intersection of G plus I and G plus J. Recall, what's the G plus I? It's the intervention units connecting to outcome unit I. This is the intervention units connecting to outcome J. And the intersection, if you talk about I and J, we worry about our common treatment units. Okay. This is the meaning of this notation. Some notation here. Why do we need them? Because if you do the derivation, you will see the symptotic variance depends on lambda 1, lambda 0, lambda tau in this form. This is 3 quadratic forms. It's a vector outcome for all ones or zeros and the cross term. Okay. And it's not that surprising we need this intersection because this is basically the second order inclusion probability. Okay. The variance formula, the first two terms are okay. The third term is troublesome. The third term depends on y all ones and y all zeros. And this term, you can never estimate it from the data. Why? Because if unit I receive all treatment, it will not receive all zeros. You can never observe both. Okay, that's a fundamental challenge of causal inference. You can never observe the potential outcomes simultaneously. There's no information. You can estimate the first two terms. You can never estimate the third term. That's a trouble term. Anyway, introducing the formula, I gave you some discussion of the condition that I cannot explain well before. If we go back to the classic setting, we can check the condition is actually standard. The classic setting, there's no bipartite graph, or it's a degenerate bipartite graph. Intervention units are the same as outcome units. Then this G is simple, just 1 or 0. The formula reduced to the classic formula you might have seen before. Okay, the condition reduces to this condition. This condition is in most time is satisfied because in most interesting settings, this Vn have order 1 over n, so this will diverge to infinity. That's the usual setting, variance 1 over n. If we go back to the setting with Bernoulli randomization over clusters, then the outcomes are clustered, corresponding to the household are connected to the villages, and students are connected to the classroom. So it's clustered. It's block diagonal matrices, and we can recover some formula we derived before. And the condition reduces to this condition. This condition slightly complicated than before, but you can read. This is the order of Vn is 1 over m. This is the m to the power of this number. There's an annoying quantity here. It's the ratio of the maximum cluster size and divided by the average size. So what does this mean? This means there's no dominating clusters. There's no cluster that's super large compared to the average. If you imagine the cluster size are pretty uniform, you can ignore this term. This term is basically constant. You can drop it. This quantifies how influential some clusters are. Okay, anyway, if you ignore this middle term, this holds for similar reasons as this. Okay, this is 1 over m, it will hold in most cases. Okay, so let's go further. We have consistency of some technical normality and the variance estimation. Variance estimation is actually the most interesting part because everybody can prove consistency of some technical normality under some conditions. Okay. We just discover those conditions. How do we do variance estimation? But the variance estimation, as I mentioned, is challenging because you can never estimate the third term. There's no hope. We can never estimate the variance, but we can estimate some upper bound of the variance. We derive an upper bound of the variance by Cauchy-Schwarz inequality. Very simple idea. You cannot estimate the variance of the difference. You just bound the variance by the marginal variances, and this is identifiable. It depends only on the marginals of y1s and y0s. Okay. You can do this, but it's upper bound. Slightly different from the literature, but it's also at least known in simple case, like complete randomized experiment. It's not known, of course, for bipartite experiment. It's known in simpler settings. Okay, to estimate the upper bound, we just estimate V1. Here, V1 and V0 is quadratic form, and we estimate the quadratic form by this double summation with indicators Ti, Tj, and this is again the inverse probability weighting. So it's not that surprising. Quadratic form with this double summation. Of course, with the lambda 1, lambda 2, lambda 0 matrices introduced. Okay. If you use this variance estimate of the upper bound to do inference, it will be conservative. So your interval will overcover. Okay, so let's move on to the next question of covariate adjustment. Also very standard question. If you want to use covariates to improve efficiency of your estimate, how do we do it? We also do it in a very, very simple, even naive way. We consider a class of linearly adjusted estimator. If you observe covariates for outcome units, I from 1 to n, of course, this is x, but actually this x can be very general. For example, this g plus I can be a part of xi. It's a feature of the graph, but also you can view it as a feature of unit I. Okay. Xi can be general. To simplify the presentation, we assume x is centered with mean 0. It's minor, but it makes discussion simpler. Consider the linear adjusted estimator mu1, mu0. Simple modification, just minus a linear combination of x in the estimator. Then you don't change anything because x has mean 0. The term you add in has mean 0. So you don't change the mean. That's why we center the covariates for this simple reason. Does that change the probability limit because of the centering? And if you choose beta to be 0, you have the Hayek estimator. This means you can have better choice of beta 1 and beta 0. There are some other choices of beta 1, beta 0 to make the variance smaller. And it's a trivial game to derive asymptotic variance formula for this linearly adjusted estimator, because you can view this estimate as Hayek estimator for this adjusted potential outcome. So the variance depends on beta 1, beta 0. The goal is to minimize Vn as a function of beta 1, beta 0. But this is not that trivial, because if you remember the formula here, there's a term you can never estimate. This term, if you have beta 1, beta 0, beta 1, beta 0 will enter this term. So how can you minimize this variance as a function of beta 1, beta 0? But there's a term you can never estimate. Okay. It seems you can never estimate, but actually, doing some exercise, simple linear algebra, you can actually show it's doable, because you cannot minimize the variance directly. You can change the game a little bit without really changing the game, changing the formulation without changing the game. You can minimize this term. Okay, you want to minimize Vn as a function of beta 1, beta 0, but minimize the difference. This has nothing to do with beta 1, beta 0. And if you can show this term can be written as this one. Okay, I think this is an interesting formula. Looks impossible, but after some simple algebra, you can show we can minimize this part. Okay, this part is trivial, it's quadratic. I'll assume everybody knows how to minimize a quadratic function. Good. And this is the one minimizer. There are actually multiple minimizers. The solution is not unique, surprisingly. You may feel this is unique. It's not unique even in simple cases. We use one solution, so I have pseudo inverse here. This is the Oracle estimator, the optimal one to minimize the variance. And we estimate the beta. We don't change this part because it's known, and we estimate the quantities here by double summation. Okay. And how do we implement our procedure? We first solve beta 1 hand, beta 0, then plug in to the linear estimator. Very easy to implement. Okay. And we can show there's no difference in the limit. The Oracle estimator and the feasible estimators are the same in the limit, of course, under some condition. And we can also estimate the upper bound of the variance using the same formula. Okay. This is the second part. Because of this asymptotic equivalence, we can show the same property of this covariant adjusted estimator. It has consistency and asymptotic normality. It has smaller asymptotic variance. But there's a lot of weird issues in design-based inference. For example, even though we can show asymptotically we reduce the variance, it's possible, if you look at the confidence intervals, it's actually wider than the naive estimator, because we are estimating the upper bound of the variance. So it's possible. In theory, you are doing better. In practice, you are doing worse in terms of the length of the interval. This phenomenon was also observed in some simpler settings. We introduced some notion called sampling precision and estimated precision. Sampling precision means the true asymptotic variance is smaller, it's more precise, but the estimated one, due to the confidence interval construction, may not be in the same direction. Okay. But you can solve this problem if you really care. We don't really care about this because we want to propose something simple to implement. If you really care about this issue, then you can minimize the asymptotic variance under the constraint. The estimated variance is smaller. Or doing the other way, you can minimize the estimated variance under the constraint. The asymptotic variance is not increased. So you can change the optimization problem a little bit, just to rule out those cases you don't like. Okay. Of course, those optimization problems are much more involved, much more difficult to implement. Here, it's really trivial to implement. There's a formula you just apply. Okay, I will try to wrap up. Maybe quickly go through a simulation because simulation never fails. I can just quickly go through them. But there's one point I want to convey via simulation. So we use their data, and this is the magnitude of M and N on the number of power plants on the region they care about. Okay, well, there's some true effect, and we use covariates to do covariate adjustment. Just one minor point I want to convey is want to make sure in theory our standard error is reduced, but there's no guarantee the estimated standard error is reduced. But in most reasonable data generating processes, you will observe they go down in the same direction. But you can challenge your estimator by constructing those examples. One is reduced, the other is increased. Okay. But maybe I go to comment on more interesting issues in the future. So some discussion. Okay. In the literature, sometimes people prefer regression-based analysis. They were saying, okay, even if our mathematics is on the design-based inference, we just want to run regression because everybody is running regression to analyze data in practice. We can show our estimator is identical. Hayek estimator is identical to weighted least squares with properly defined weights. We can also include covariates in weighted least squares, and regression can even provide robust standard errors. And we did it for another network experiment. But here, if you use it, there's no guarantee it will be correct. Why? Because when you run regression, if you don't use second order inclusion probabilities, then regression will never use that information. Then regression can never recover the variance estimator we want. Because the variance estimator, if you want it to be correct, it must involve second order inclusion probability. But then probability never enter the regression. Okay. Of course, you can say, okay, if you really want to use that information, then let's force our regression to use the second order inclusion probability. Then it's possible we can solve that problem. But that's not a standard regression you would like to run. Okay. I think it's interesting. It's still open problem. How do we unify this to two views? And other issues on estimates and estimation strategies. Here we estimate tau. It requires basic assumption. You have enough data. You have enough units with all ones and all zeros on the intervention side. The width will shrink to zero exponentially fast in G plus I. In bipartite graph, if you don't have enough sparsity, if you have large degrees of G plus I, then it's possible you can never obtain even consistent estimator for tau. Then we will have to make assumptions, or you need to change your problem. For example, you have to assume your potential outcome, Yiz, not depending on the whole vector, maybe depending on a low dimension summary of the vector. One example is Di. Di is the proportion of treated units connecting to me. That's one standard assumption people would like to impose. Then it's possible you can make progress here, but it's a restriction on the dose response curve. Okay. And currently we are thinking about extension to two-sided randomization. In this talk, I focus on randomization on one side. When I was talking to the online platform people, they were saying they have randomization on both sides. They have randomization on producers, also have randomization on viewers, because we are receiving YouTube advertisements all the time. That's why that's the randomization on your side. Then we have randomization on the producer side. Okay, this is the two-sided randomization. And this is interesting extension of classic factorial experiment. It's a 2x2 factorial experiment. And in the classic literature, one special case is called split plot experiment. What split plot experiment is? You have clusters. You have units nested within clusters. You randomly assign some factor to clusters. You also randomly assign some factors to the units. Okay, so the teachers receive one treatment, maybe higher or lower salary. I don't know whether that's ethical. And the students receiving another randomization, maybe using iPad or not. So you can imagine there are two factors, but randomization at different levels. Okay, in the agricultural world, they call it whole plot and subplot. The whole plot is larger area, and subplot the smaller area, due to logistic restrictions. But I think this setting has interesting application in modern experiment. We view this as an extension. Oh, sorry, where is it? Oops. We view this is extension of split plot experiment to the bipartite world. If you agree bipartite on one side, randomization is extension of cluster randomization, then you are okay with this analog of split plot. But I think it's very non-trivial extension. A lot of rich research questions going on. It's extension of factorial split plot, also bipartite. You can measure outcome on both sides, and also you can measure outcome on the edge. Okay, so there are many parameters we can discuss. It's related to something called multiple randomization design proposed by Amazon people. They are thinking about randomization to buyers and sellers. Okay, you can have this randomization.